Hello everyone. So this is the first exam preparation session I'm going to conduct with you. Okay, I have prepared 4 practical problems that we have to solve today. Now, for the record, you guys are going to have questions on direct kinematics, inverse kinematics, differential kinematics, which contains Jacobian matrices and singularities. You are going to have some, some theoretical questions on redundancy, and what else? Yeah, maybe some theoretical questions on singularity and stuff like that. And what was the last lesson? I think that's it. And of course, trajectory planning. Okay, so this is more or less what you are going to have in the exam, and of course some fundamentals will appear in the exam next week. Okay, I think the biggest challenge in the upcoming exam is the practical part, which basically covers direct kinematics plus differential kinematics. Now, I have prepared 4 problems that we are going to solve today, just to give you some ideas what I want from you to write in the exam. Okay, you will be provided with such a manipulator that you see on the screen, right? We have a prismatic joint, we have another prismatic joint, and we have a revolute joint, which is followed by an end effector. Now, the first question says, write down the parameters according to the Denavid-Hartenberg convention and fill in the relevant parameter table. We are talking about this DH parameter table. Now, first step is to assign the frames. Now let's try to do it. We know the frame assignment, right? We know how the X, Y, Z axis should be assigned to each joint, let's say. Okay, we have to start with the joint with the base frame, right? Which is in our problems we usually take base frame and the 0th frame the same. Okay, some literatures separate them, but in our problems, I mean, for convenience, we usually take them together. Okay, so let's say my base frame is going to be right here. I mean, let's say on this surface, okay, and particularly in this particular point right here. This is the origin of the frame 0. Z0 axis should be in the direction of the movement of the prismatic joint, right? So it corresponds to this axis, to this direction. So this is going to be Z0. C0. Okay, what else? Then we can have X0 in this direction, which is parallel to this axis, right? Okay, I'm gonna do my best. So this is going to be X0, and using my right hand rule, I know that my thumb points to the direction of X0, right? And my middle finger points to the direction of Z0, and automatically, as a result, Y0 will be directed to this particular direction. Something like that. Okay, and this is going to be Y0. That's it. So this is my base frame, the frame 0. Okay, now I have joint variables as well, right? Let's say this is D1. We know that the joint variable for the prismatic joint is D, right? The distance that the prismatic joint moves along. Okay, then we have another joint, which is again a prismatic joint. D2 is the joint variable for the second joint. And finally, my third joint is a revolute joint. I'm talking about this one, And the joint variable for this particular joint is going to be what? Theta 3. Okay. Okay, now let's move on with the frame assignment. Okay, we are in the second joint now. Okay, we know that the Z1 direction should be the direction of the movement of the prismatic joint, or the direction of the translation of the prismatic joint. It can be either this direction or this direction. I'm going to choose this one, right? Okay, let's choose it. It's going to be Z1. What about X1? X1 should be perpendicular to both Z1. Let me write it down right here. It should be perpendicular to both Z1. It should be perpendicular to Z0. And it should intersect the previous Z-axis, which is Z0. Okay, X1 should intersect the Z0 axis, right? So this is the reason why X0 will be something like that, you know, parallel to Y0. So it's going to be what? X1. Okay. I have Z1, I have X1, and I don't really need to show the Y1 axis because, you know, it's too much information in our case, so we don't really need it. Now, let's move on to the next joint, which is a revolute joint, and we know that the Z-axis should be chosen in the direction of the rotation axis, or the generally Z-axis is the direction of rotation, or axis of rotation, which is either upwards or downwards. Okay, I'm going to choose the up direction, so it's going to be something like that. Okay, so this is my Z2, and what about X2? Now, intuitively, I can choose X2, this one, right? But no one guarantees. Okay, let me put it this way. No one guarantees that X2, the X2 axis, right? I know that X2 is perpendicular to Z2 right here, but no one guarantees that it will be perpendicular to Z1. Okay, X2 is not guaranteed to be perpendicular to Z1. Okay, because we know that it's, let's say this is Z1, right? And if X1 is perpendicular to Z1, X2 should be, okay, it should be parallel to X1, you know, these two lines should be parallel to each other so that X2 can be perpendicular to Z1 as well. Okay, so that's why I cannot really draw X2 in this particular direction, but I have to draw X2 parallel to X1. Okay, that's why it's going to be something like that. No, it's not so accurate, so it's going to be something like that. Okay, it's going to be X2. That's it. That's it. All right. Now let's move on to the end effector, and I know that we usually copy the Z-axis from the previous joint. Okay, when we assign the frame for the end effector, so it's going to be what? So this is going to be my Z3, right? And what is the rule for X3? It should be perpendicular to C3, and it should be perpendicular to Z2. At the same time, it should intersect Z2. So it's going to be a line. It's going to be a line along this link so that it can intersect the Z2 axis. Okay, this is frame assignment. We are good. Now we can actually move on to the DH parameter table. Okay, frame assignment is done. We can move on to the frame assignment table. Now, this is the DH parameter, DH parameter table. Now this is the table we are talking about. Now let's try to fill it in. Now, this is A, right? What is the question for A? let's remember. So A1, we are talking about this one. Um, okay, like how much I have to move the origin of frame 0, right, along x1, to align the origin of frame 0 with the origin of frame 1. As you can see, the origin of the frame 1 is the 0th point of x1, right? But at the same time, I know that the origin of frame 0, again, as well, is the 0th point of the same x1 axis. So we don't really need to move the 0th frame's origin along x1, okay? So because both of the origins are at the same point of this particular axis. So there is no need for any translation of the origin. So it's going to be 0. Okay, now let's try to find what? A2. The question is, how much? Okay, along x2, the question is along x2 in this direction, right? How much I have to move, oh my goodness, how much I have to move the origin of the previous frame, which is frame 1, okay, to align it with the origin of the frame 2. So again, both of these points are the 0th point of x2 axis. So there is no need for any translation along x2 direction. So it's going to be what? 0 again. Now, unfortunately, I didn't write the link length right here. So let's say this particular link is A3. Okay. Okay, now let's ask this question again. I mean, for A3. To find A3, we have to ask this question. Along x3, along axis x3, how much I have to move the origin of frame 2 to align it with origin of frame 3? The question is A3, right? This is x3, right? I have to move it in this direction. I have to translate this point by A3 so that they can both align with each other. Okay, so the answer is A3. Okay, that's it. Now let's move on to the next parameter, which is alpha. Okay, the question for alpha is, again, we are working with let's say x1, because we are going to find alpha 1. So around x1 axis, see that? Around x1 axis, right? How much z0 should be rotated, okay, so that it can align with z1? Okay, so the answer is pi by 2, 90 degrees, because again, using our right hand, okay, x1 shows my thumb. This is my thumb, and this is my forefingers. Okay, the direction of my forefingers shows the positive rotation. Okay, it shows the positive direction of the rotation along x1, right? So it should be, x1 should be rotated by 90 degrees. Okay, let's say z0 is here, right? It should be flipped 90 degrees so that it can align with x1, z1, and this is positive direction, pi by 2. Okay, let's move on to the next one. The question is for alpha 2. For alpha 2 is the question is around x2, how much z1 should be rotated so that it can align with z2? Okay, this is kind of opposite. It should be actually flipped back to the let's say erected position, right? So, and this is the negative direction. So it's going to be minus pi by 2. Again, using my right hand, I can actually detect the direction of positive rotation. Okay, now we are going to find alpha 3 here, right here. Okay, what is alpha 3? The question for alpha 3 is around x3, how much I have to rotate z2 so that it can align with z3. The answer is what? 0, because they are already aligned. They align with each other because they are parallel, right? So it's going to be 0 for alpha 3. Good. Now, let's move on to the next variable, d1. Now, to find the, let's say, value for d1, we have to ask this question. Along z0, right, how much I have to translate the origin of frame 0 to align it with origin of frame 1? The answer is pretty simple and pretty straightforward to see. The answer is d1. You have to move or translate this point by d1 to align it with the origin of frame 1. So the answer is d1. Okay. Now let's move on to the next one. To find d2, let's ask this question again. Along what is that, z1? Yeah, along z1, how much I have to move the origin of frame 1 to align it with the origin of frame 2? The answer is d2. Okay, let's write it down right here, d2. Okay, now let's ask the same question for the last bit. So we are going to find d3. The question is, along z2, how much I have to move or translate the origin of the second frame to align it with the origin of the third frame? The answer is 0, because they are already aligned. Both of these origins, right, are at the 0th point of the z2 axis. So there is no need for any translation along z2 axis. Okay, finally we are in theta 1. Let's try to find it, find what theta 1 is. The question for theta 1 is around, now we are talking about angles, so around z0, which is this axis, right? How much I have to rotate x0 so that it can align with x1? The answer is positive 90 degrees. Again, using the right hand. This is my right hand, right? Thumb, the direction of z0, and let's say the direction of the 4 fingers, right, shows the direction of the positive rotation. So this is basically x0 rotated or flipped to x1 by 90 degrees, and this is going to be positive pi by 2. Now we are going to find what? Theta 2. What is theta 2? What is the question for theta 2? Okay, the question is around or about z1, how much I have to rotate x1, by what angle I have to rotate x1 so that it can align with x2. As can be seen, they are already parallel to each other, right? So there is no need for any rotations around z1. So it's going to be 0. Now, for the last one, we have to ask ourselves one question. We are finding theta 3, sorry. The question is, along around z2, right? How much I have to rotate x2 so that it can align with x3? This is obvious, and the answer is theta 3. Joint variable theta 3. So this is all about my DH parameter table. Okay, we assign the frames. We have the, what was that? DH parameter table. Now, let's move on to the next question. The next question says, for the given manipulator, write the direct kinematics equations of the position only. Okay, so let's try to do it. And there is a hint, or there is a remark below. If you consider it useful for solving the exercise, remember the expression of the homogeneous transformation matrix between two consecutive triples, or two consecutive frames. Instead, like you can, I mean, it's kind of a wrong word used. It's just two consecutive frames. Okay, this is the one. So basically, in the first statement, we are asked to use the geometric inspection, which is easier to realize. Geometric inspection, okay, to find the position vector. We are basically asked to find the position vector of the third frame with respect to the frame 0. Okay, third frame with respect to the 0th frame. In other words, where this origin is located in this particular frame. Okay, this is the question. Now, we have two methods to realize this question, to solve this question. The easier method is, of course, using the geometric inspection. Let's try to do it. Now, geometric inspection is all about reducing the dimension of the manipulator to degree of to the planar view, or to the 2-dimension. Okay, now let's try to have a look at this picture. Let's have a look at this picture from above. Okay, assume that your eye is right here. This is your eyelashes. So this is your eye, and you're having a look at this image from above. Okay. Okay. What do we see in the first sight? At the first sight, we see y0 and x0. We cannot see this, let's say, upward pointed axis, right? And you can see what you don't see this prismatic joint, but you see this one. Okay, you see this particular link length, and you have this joint. Okay, you have to give some sort of angle to it so that you can actually make it a bit more convenient, right? Then you will see the this link, right, with the end effector. So when you have a look at this picture from above, this is all you see. Now let's try to translate what I just said to paper. Okay, first things first, you see the y0 and x0 axes. Let's draw it right here. Okay, this is y0, this is x0. It was too much. Okay, y0, x0. Okay, then I have what? I have this this length, right? So it's going to be d2, right? If I start right, if I actually draw it from here, I have this length along x0, right? Okay, let's draw it. Okay, let's assume that this is my d2. Okay, then we have a revolute joint. We have a revolute joint right here. And the theta, okay, I have to find what is theta, because this is the most tricky part. This is the trickiest part because it's the most confusing one. Okay, assigning theta 3 angle in the right way. Okay, so I know that the angles usually are are the ones, right, between the link and the x-axis. Okay, let's assume that my x-axis is something like that. Okay, this is my x2 axis. I'm talking about this one. Okay, and well, with my positive rotation is this one, right? This is my positive rotation along z2. This is my positive rotation using my right hand hand rule. Okay, now if I give up on the idea to draw this link in this position, okay, if I don't really draw this in this particular position, but in this position, okay, I do not lose anything. So it was something like that. Let me see. It was something like that, right? But I don't draw it this way. I draw it this way, and I have a right to do it. Now, this angle is going to be positive theta 3. Okay, that's it. And this is, have a look at that. This is A3. So I write it here, A3. That's it. And this is my point P, which shows the end effector. That's it. So this is the two-dimensional version of this manipulator if you have a look at it from above. Okay. Now, what do we see here? We can actually, let's say, draw some conclusions on px, right? Px, this point, and py, this point. Now, using simple px is going to be equal to what? Now, this is px, right? It's going to be equal to what? d2 minus this particular length, because we are interested in this one. The whole length, d2, right, minus this particular length or this side of this triangle. Okay, so d2 minus okay, what is x? Okay, let me write m. What is m? Well, m is a3 sine of theta 3. That's it. So px is going to be d2 minus a3 sine of theta 3. What about py? What about py? I'm talking about this one, this point. So it's going to be what? This side of the triangle. What is that? a3 cosine of theta 3. That's it. Now, I know that the position vector P is Px, Py, and Pz, right? I have two of them. I found this first two. Now let's try to find Pz. You cannot see it here because we don't really see it in the two-dimensional, let's say, representation. But if you have a look at this picture from a side, right, you will see that this point is away from the, let's say, let me put it this way. Okay, let me put it this way. This point corresponds, right? This point corresponds to the, let's say, oh my God, how can I put it in the right way? P0 is D1 distance away from the origin, okay? Origin of the zeroth frame along Z0, okay? That's it. So P0, PZ, sorry, is equal to D1. That's it, okay? Because if this joint goes up and down, or if it makes the end effector goes up and down, right? The PZ value, which is the component, let's say the projection of this point along Z0, okay, it changes as the D1 changes, okay? So we conclude that PZ is equal to D1. That's it. That's it. Now this is my position vector. Okay, so position vector is equal to what? D2 minus A3 sine of 3 sine theta 3 A3 times cosine theta 3 and D1. That's it. Nothing else. Nothing else. So it's all about geometric inspection. Nothing else but geometric inspection. But if you hesitate, if you have some doubt on solving this problem, right? You can use, let's say, conventional method or systematic method to find the joint variable. Sorry, to find the position vector. We know that a transformation matrix consists of 4 parts. We have standard zeros, we have 1, right? And this is the position vector, and this is the rotation matrix, right? So you are asked to find the position vector, right? P3 with respect to P3 to 0, right? Which shows the position vector of the frame 3 with respect to the frame 0. Now, where is this vector located? It's located in this transformation matrix, which consists of rotation matrix of the 3rd frame with respect to the 0th frame, position vector of the 3rd frame with respect to the 0th frame. We have zeros and 1, okay? So you have to find out, you have to determine this particular matrix. Now, this particular matrix, according to the decomposition rule, is going to be equal to A1 to 0 times A2 to 0 to 1 times A3 to 0, 3 to 0, sorry, 3 to 2, okay? So using this one only, okay? Multiplication of the 3 matrices, right? You will find A3 to 0, from which you can find the position vector of the 3rd frame with respect to the 0th frame. This is a procedural solution. It's a systematic solution. It's going to take a lot of time, but just to be on the safe side, you can use it, okay? So if you do not really rely on your geometry or your imagination, you can skip this part, okay, which is geometric inspection, and use the conventional method or systematic method, okay? So no one stops you from there. And in the exam, I'm going to provide you with this equation, okay? So if you want to find A1 to 0, all you have to do is to take the first row of the DH parameter table and substitute all these values to this matrix. That's it. Again, if you want to find out this matrix A2 to 1, you have to take the 2nd row, and the 3rd row will be used for A3 to 2, okay? Which will, after which you are going to multiply, let's say these 3 matrices by each other. That's it. That's it. Okay, I think this is all about let's say direct kinematics or forward kinematics. Now let's move on to the differential kinematics. Okay, in the last statement, it says, for the given manipulator, determine the geometric geometric Jacobian, highlighting the singularity points relating only to linear velocities. Okay, now this is a problem we have to cover in differential kinematics. Okay, so we know that well, we are going to have what is the size of the Jacobian matrix in this particular case? We know that the Jacobian matrix is a 6 by n matrix, right? Where n shows the degrees of freedom of a single manipulator. In our case, we have a degree of freedom manipulator because we have 3 joints: prismatic joint, and revolute joint. So 3 degree of freedom. So our Jacobian matrix is going to be what? 6 by 3 matrix. Okay. Now let's try to synthesize a Jacobian matrix for this particular manipulator. Okay. Let's try to do it. Okay. Jacobian matrix, J of Q, right? We know that it's a function of joint variables, right? So J of Q is going to be equal to what? It's going to consist of 3 columns because we have 3 joints. 1, 2, and 3 columns. And what types of joints do we have? Prismatic, and revolute, right? For the prismatic joint, we know that the formula is for the linear components of the Jacobian matrix, we have to use zi minus 1, right? So I is 1 in this case, so 1 minus 1, z0. And the prismatic joint does not really produce any angular velocity, right? So that's why it doesn't have any angular velocity components in the Jacobian matrix. Now let's move on to the second column. Again, the second joint is a prismatic joint as well, right? So again, we are going to repeat the same formula. Zi minus 1, in our case, I is 2, so it's going to be z2 minus 1, z1, right? And again, it does not produce any angular velocity components, that's why it's going to be 0, right? Now, finally, the third joint is a revolute joint. The formula for the revolute joint is what? Zi minus 1, which is z2, cross product p and effector, right? P minus pi minus 1, which is p2. That's it. This is all about linear velocity of the revolute joint, right? And the angular velocity is going to be zi minus 1, which is z2. Okay, that's it. So this is the general, let's say, view of the Jacobian matrix of this particular manipulator. Now let's try to find out the unknown components. Z0 is going to be 0, 0, 1, right? Now, we know P0, this is 0, 0, 0. It's very, very clear why we have this. Let's say values, we automatically write them down because we know where they have come from. Okay, now, we don't really know what is Z1. We don't know what is Z2. We know P because just right here, we found P. Okay, using the inspection, geometric inspection, we found P, but we don't know P2. We don't know P2, and we don't know Z2 either. Okay, now, let's start with Z1. Let's have a look at this image. Z1, right? So, as a vector, Z1 lies along the x0, right? So, the projection of Z1 along z0 is 0. Okay, it doesn't have any projection on z0, on y0, and I know that this is completely lies. It's completely lying along the x0 axis. So that's why it's going to be 1, 0, 0. P1. Sorry, C1. It's going to be 1, 0, 0. So we found it. We found it. Now, what about Z2? Let's have a look at it. Again, we are actually doing everything with respect to the base frame. Now, Z2, right? Z2, the projection of Z2 along Y0 is 0, along X0 is 0, and it completely lies along the Z0 axis, right? So it's going to be 0, 0, 1, because they are parallel to each other. So Z2 is going to be 0, 0, 1. That's it. That's it. Now, so this is done. This is done. We know this. What about P2? Now let's try to find P2. P2 is this point, right? This point. So in this particular picture, though, this is P2, right? No, sorry, this is P2. This is P2. Okay. So the P2 is going to be equal to what? What is Px? Well, I think Px is going to be D2 completely. D2, the whole, where is that? The whole thing. Okay, you don't really have to deduct or reduce this portion. The complete D2 will be my P2x. Okay, what about Py? Sorry, P2y. This is going to be 0. Have a look at that. This is 0. This point. Okay, 0. And what about z? Have a look at that. The same thing for P2z. Okay, whatever you told about P3, or let's say end effectors z component, you can tell the same thing about the z component of this origin, right? So they are the same height with respect to the 0th frame. Okay, so it's going to be D1 as well. D1 as well. Okay, now let's try to substitute all these variables to the to this formula, Jacobian matrix formula, let's say. Okay, now let me write it down here. P minus P2 is going to be equal to, so this is P, and P2 is this one, right? Okay, element wise we have to subtract them. So D2s are cancelled. We are left with A3 sine of theta 3. Then we have this element minus 0. So we are left with A3 cosine of theta 3. And we have D1, right? Minus D1, 0 for the loss component. Okay. So let's substitute everything here. J of Q is going to be equal to, what is Z0? Z0, right? 0, 0, 1. Then we have 0, which is 0, 0, 0. Okay, because the dimension of the Jacobian matrix is 6 by 3 in our case, right? So 6 rows. Okay. Second column, Z1. This is Z1. 1, 0, 0. And then we have zeros. 0, 0, 0. Okay, now we are in the third column. Z2. This is Z2. 0, 0, 1. Cross product. P minus P2. P minus P2. This is P minus P2 minus A3 sine of theta 3, A3 cosine of theta 3, and 0. Okay, then we have Z2, which is 0, 0, 1. 0, 0, 1. Okay. Now, I cannot do anything here because they are done, but I have to simplify this one. It's a cross product. Let's remember let's recall how the cross product should be realized, should be performed. So if we have A1, A2, A3 cross product B1, B2, and B3, so we have here A2 times B3 minus B2 times A3, A2 B3 minus A3 B2. Then A3 times B1 minus A1 times B3, A3 times B1 minus A1 times B3. Okay, and finally A1 times B2 minus A2 times B1. A1 times B2 minus A2 times B1. Okay, that's it. Now if we apply this formula to this part of the matrix, we get what? 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. Then we have, minus A3 cosine of theta 3, and minus A3 sine of theta 3, 0, 0, 0, 1. That's it. That's it. Okay, then we have Jacobian matrix. Now this is the final Jacobian matrix. That's it. If you are asked about, for example, you can actually get a question. You can get such a question. Okay. Okay. Write the, let's say, linear velocity equation along x0. Okay, you can get such a question. Now, to answer this question, you have to understand what Jacobian matrix is. What is the purpose? What is the definition? What is the physical meaning of Jacobian matrix? Jacobian matrix basically relates the joint velocities to the linear velocity and angular velocity of the end effector. Okay. Now, this is what Jacobian matrix does. This is the physical meaning behind it. Okay. Now, let's see. Let's say this is V and omega, right? So both of them have 3 separate components. V is linear velocity. Linear velocity along what? Linear velocity along x0, linear velocity along y0, and linear velocity x0, y0, and linear velocity along z0. Okay, these three px, py, vz are the linear velocity components of the end effector. Right? Again, we can say the same thing about what? Angular velocity of the end effector around x0, around y0, and around z0. Okay, so both of these two types of velocities have 3 components: omega x, omega y, and omega z. Okay, this is the same thing as this one. Now, this, let's say, end effector velocities are equal to Jacobian matrix, right, times what? Joint velocities. What is my joint variables or joint velocities? This is D1, right? So its velocity will be d1 dot. d2, right? d2 dot will be the corresponding velocity. So this is theta 3. Theta 3 dot will be the corresponding velocity, angular velocity of this particular joint. So d1 dot, d2 dot, which stands for the derivative, and theta 3 dot. Okay? So if you have to answer the previous question, which says write down the equation for the linear velocity along x0, so you have to do what? You have to take Vx, right? And the corresponding rows and the columns of the right part. So the first row, and the whole joint velocities. Okay? So Vx is going to be equal to 0 times d1 dot, which is 0, plus 1 times d2 dot, plus this let's say term times theta 3 dot. Okay, so d2 dot minus a3 cosine of theta 3 times theta 3 dot. Now this is the equation. This is how we can find the end effector's linear velocity along the x0 axis given the joint velocities. Okay, such an interesting practical example. And finally, we can ask to find the singularity, let's say point or singularity of this particular manipulator, only relating to the position. Okay, which means that let me transfer my Jacobian matrix here. Now this is my Jacobian matrix, right? This is my Jacobian matrix, J of Q. I know that J of Q actually consists of two portions, JP of Q and JO of Q. The first three rows actually corresponds to the linear velocity component, while the last 3 rows are related to the angular velocity of the end effector. Okay, so that's it. So if you're coming back to the statement, it says highlighting the singularity points relating only to linear velocities. Okay, so you have to separate the linear component of the Jacobian matrix. Okay, and you have to find the determinant of this particular portions, which is JP of Q. Okay, now let's try to do it. So JP is what? 0, 0, 1, 1, 0, 0, minus A3 cosine of theta 3, minus A3 sine of theta 3, and 0, right? So you have to find the determinant of JP. What is the determinant? Well, I can take this row. So it's going to be what? Only 1 times, right? 1, 0 here, minus A3 cosine 3 here, minus A3 sine of 3 here. And here, 1, 1, 2, 3. Oops, sorry. 1 and 1, 2, 3. Okay. If you do not really know how we calculate the determinant, try to review your knowledge on this topic. So this is a positive times minus, I mean, positive 1 times positive 1. So ones are just gone. And we have here what? AD minus BC, right? Yes, AD minus BC times the multiplication of these two minus product of these two. So we are left with A3 sine theta of theta 3. That's it. So, and after finding determinant, you have to equate it to 0. Okay. So what is the result? What is the solution? So sine of 3 should be 0, which means that theta 3 should be pi, or theta 3 should be 0. Now these two are the singularity points of this particular manipulator. That's it. That's it. I hope you enjoyed this session. This is just the first, only one problem out of 4. Unfortunately, I cannot really go further. I will definitely upload another problems because I have prepared them as well. I'm going to solve them and share the solutions with you because it's too late in the morning. I have to sleep. I'll talk to you soon. Bye.